Metastannic acid reforming and scrap tin recycling. In the realm of scrap tin recycling, all efforts are extended to sort and sell any of the clean, readily remeltable tin alloy scrap, thus reducing the total volume of remaining residual or complex mixed materials. A method may be adopted for extracting values from the remaining leftover tin content scraps, including such items as solder and solder dross, tin-plated items, and tin-bearing residues. By leaching mixed residues, that contain various concentrations of tin, with an acid solution that may readily dissolve the metal into an ionic solution, you may begin to isolate the tin values. Dissolving tin in a solution such as nitric acid results in an immediate reaction, transforming the tin into a substance known as metastannic acid, which is a hydrated tin oxide. Reforming metastannic acid, by the reduction back into metallic tin, is somewhat of a sticky challenge to convert the gelatinous stannic oxide, but may be achieved in a multiple-step process. Metastannic acid, H2O3SN, is an inorganic, synthetic compound in colloidal suspension as a hydrogel, that requires drying or dehydration to remove the water, roasting to remove excess oxygen, and reduction to convert the metal oxide into a pure metallic form. The concept of an autothermal reactor may converge multiple individual steps into a three-stage process that achieves the metastannic acid reforming, to produce reduced metallic tin from the original feedstock of scrap residues. The three-stage processes are: 1. Oxy-combustion to generate heat and carbon monoxide. 2. The dehydration of metastannic acid to form tin dioxide, and 3. The reduction of tin dioxide into metallic tin. Now, let's look further at the different stages. The first stage is oxy-combustion to generate heat and carbon monoxide. In stage 1, the primary oxy-combustion process results in the generation of both the required heat and carbon monoxide to drive the overall three-stage process. By limiting the stoichiometric blend of oxygen supplied during the combustion of pure carbon powder, you can force an incomplete combustion reaction. This generates the required process heat while producing high yields of gaseous carbon monoxide. Next is stage 2, the dehydration of metastannic acid to form tin dioxide. In stage 2, the dehydration step is where the wet incoming metastannic acid is essentially dried and roasted to produce pure tin dioxide. The heat required to dry this material is derived directly from the exhaust of stage 3. The stage 2 process generates a steam byproduct, which may be vented through a contained exhaust into the water steam pipeline and a steam condensing engine. And finally, stage 3, the reduction of tin dioxide into metallic tin. In stage 3, the dry tin dioxide produced from stage 2 undergoes a reduction into metallic tin in a reaction with the hot carbon monoxide gas, which was generated in step 1, and acts as the primary reducing agent, stripping the oxygen from the tin dioxide to yield liquid or solid tin metal. The melting point of metallic tin is 232 degrees Celsius, but tin dioxide requires temperatures in the range of roughly 1000 to 1200 degrees Celsius to break the oxygen bonds. The required heat may be supplied from the stage 1 oxy-combustion reaction. The carbon monoxide bonds with the oxygen, that is stripped from the tin oxides, which forms a CO2 exhaust gas. The contained CO2 exhaust may be vented directly into the CO2 pipeline that may be regenerated. So an effective metastannic acid reforming system, in a streamlined autothermal reactor, may successfully be deployed to improve the recovery of tin and tin residues. We intend to explore other types of scrap metals and materials recycling, at some point in the future. Until then, please feel free to visit us at www.waste.net.